you have the definition of statistics, and you'll see kind of like 4 marks there. So our 4 areas that we are going to look at in statistics. So when you think, what is statistics? These are the 4 things we're going to study this year. First off is how to collect data. If you do a bad job collecting the data, and you give that bad data to the best statistician in the world, their results are still going to be bad. You have to get good data in order to get good statistics. If how you select your data, and we'll talk about how to do that as we go here, that'll be kind of be the first chapter we look at, is how do you select good data to get good results? If you start off with bad data, then there's nothing you can do. Second is how you organize that. If you just get a long string of numbers, that's really hard to pull information from. How do you organize that data you've collected to be meaningful to you? And we'll do some labs in here that could be with just as simple as, you know, going back to middle school and younger things by doing bar charts and tables and graphs and all that kind of stuff. Some more complicated, some not really that much more complicated than what you've done before. That's one way to visually kind of organize it. The second way is to kind of analyze it. So once you have it organized, put in order, right? We'll talk, it's not until the next chapter. It's chapter 2 where we get into things like mean, median, and mode, right? Where you maybe have to put them in order to be able to figure that stuff out. Analyzing what those are some basic things. You have other things like standard deviation and variance and other stuff that maybe you've heard of before, maybe you haven't. Those are things where you're kind of analyzing what the data is giving you, what it's saying. And then once you do all that, the third thing we do is we interpret it. What is it telling us? And if you think back to our stick figures exercise we did on Friday, some of you moved up to this higher level, like the interpret. You know, the groups that said, like, you know, all the soccer players wear Converse, right? You are now going beyond just describing or organizing the data. You're actually analyzing it or making decisions and interpreting what it's telling you. That's like the next step. We have so much data nowadays. How do we use that data is really the hard part, right? How do you make decisions by that? I know, I think of that, we were doing our game plan for the our football team last night, and we have video from the other teams, right? And we have all this data of all the plays they ran and when and what they do. And to try to like look at all of that data to then come out and say, oh, this is what we need to do. It's almost overwhelming how much data there is, right? It's like when we look at student test scores. And we have all these test scores of all the students and how everybody has answered on every single question. There's a lot of really good stuff you could pull from that. But on the other side of that, that's so much data. It's so overwhelming. It's hard to see what's going on because there's so much there. And that's when this kind of stuff becomes really important. How can you narrow down that data to be something that's valuable and useful when you just have floods of it, as we talked about last week, that they're collecting? How do you do that to be able to figure that out, right? That comes down to like that Target example, right? That they figured out, okay, people buying these vitamins and this, likely they're pregnant. That's the harder part, is making those kind of interpretive decisions when you get bombarded with all this data, right? All right. Why statistics? Last week was really about that. Just all the places that data's, you know, in the world we're bombarded with this. For those of you that are maybe thinking of, if you go to college, what you want to major in, you are actually less likely to take statistics if you go into a math or science field. I went to college, that was a long time ago, but I went to college. I didn't take a statistics class to get my math degree. Didn't have to take one. Wife went into engineering, math, didn't have to take statistics class. The people that take statistics are people that are going into like education, sociology, psychology, those kind of courses, business. those kind of, not, I don't say non-science, I don't mean it that way, but not the hard science of physics, chemistry kind of science. But those other ones, they're more likely to take statistics because they use that so much in their field and in their study, doing research and stuff. So nowadays, statistics is pretty common. I know a lot of places, if you go to University of Akron, for example, you have to take a math class to graduate. Most colleges are that way. And you have two choices. It can be a college algebra class, or it could be a statistics class. Your choice. Some places, I know University of Findlay, everybody has to take this statistics class to graduate. It's the requirement for everybody at their college. So statistics is becoming more and more and more important in all areas, and many colleges have gone to say that's the class you have to take to graduate is statistics. And if you're getting CCP in here, hopefully that will count. Sometimes they'll make you take it in your major. If you're going to be a business major, they'll make you take business statistics. If you're going into nursing, they may make you take like a medical. Basically, all that does is like all the examples you do in the class are all focused on your area. You know what I mean? They're not just general. They're all focused very specifically. So anyway, why statistics? All right, some branches of statistics. These are the two big things we're going to look at. The first one, descriptive statistics, and I have the bottom thing in your notes because it's easier to say. It's the collect, organize, and analyze part of statistics. It's the branch of statistics that involves organization, summary, and displaying the data. All you're doing is saying, hey, we collected the data, here's what we've got. We're not doing anything with it necessarily. We're not making decisions. We're not saying, hey, what does that mean? We're just saying, here's what we got. Okay, that's the first part. And then the second part is the inferential statistics. And this is the interpret part of statistics. This is the part you use to make decisions and figure stuff out. This is the part when you think about statistics. If I would ask you when you walked in here today and said, you know, what are statistics? What is statistics? This is all the stuff you've done before. Mean, median, and mode, and bar charts, and all that kind of stuff when you think about statistics, right? This is why statistics is so important, the inferential part. This is the part that if you go major in psychology and they do statistics in that, they're using the inferential part. This is the part you make decisions and you decide stuff, comes from there. All right. If you think about our getting to know the class, right? And think about all the questions that you have on here. If you think about all those questions, all the numbers and the information we recorded here are various forms of data. If I just had four numbers, 3, 7, 35, 19, that's not data by itself. It has to represent something. It has to represent the number of states, let's say, you visited. And those four numbers, right? I had somebody in the earlier class today. I was like, how can somebody visit 35 states? There's not even that many states. And I was, okay. So, so the rest of the class pretty much was not kind to him. But but once that data has like a label on it, has units on it, describes something specific, that becomes data. Okay. Data consists of information coming from observation, counts, measurements, responses. I always use the term measure, but sometimes if it's, do you smoke, yes or no, that's not really a measurement. It's just an observation. Okay. And the answers to these questions reveal one of the most fundamental principles of statistics. If you only understand one thing out of today for the rest of the year, it's going forward, it's this. All of these things, one of the most important things in statistics is variability. The idea that things change and vary as you go through. If something doesn't vary, there's really no statistics you can do with it, right? It's like, let's say I gave each of you a quarter to flip, and I told each of you to flip it 100 times. Now, what's the probability of heads and tails when you flip a coin? 50-50. So therefore, every single one of you should have 50 heads and 50 tails. If every single one of you had 50 heads and 50 tails, what would be your first thought? What would be my first thought if I saw that? You probably lied and you just wrote down 50-50, right? Now, is it possible that a few of you may get 50-50? Yes, But the idea of statistics and variability is I would expect somebody in here to have, 40, 60. That's possible and wouldn't be that unusual. Maybe even a little bit less than that, 35, 65, even something. The idea of variability is even though it's 50-50 and that's the percentage, when you actually do that or you get in the real world, statistics is so much about the real world, and you actually flip it, that's not exactly what's going to happen, right? It's going to vary, and that's okay. Just because you get that variation doesn't necessarily mean you did anything wrong. That's just how things work, right? You get that variability. All right, some more definitions. The idea of an individual, the person or object included in a survey. And the variable is a characteristic of the individual to be measured or observed. Think back to our stick people from Friday. Each person was the individual. And I can't remember all the names now. Each card, each person was an individual that was being measured or observed. And then all the information on that card, the height or the sports or the shoes or whatever it was, that was what was being measured. When we did this, what was the individual? Or who was the individual? You were, right? And then each of these was a variable being measured. Now, some of these, such as who's your statistics teacher, was not a variable because it didn't vary. Everybody said the same thing. Okay, so that's that idea. Variable and individual, okay? We have two types of variables. We have quantitative data or qualitative data. Now, I understand where the two names come from, but I also feel like whoever came up with these decided to try to make things confusing for you, because why do they both have to start with the same three letters? And it's easy to get confused. So when you think of these, I like to think of, really, I will use the term a lot of time for qualitative data. I would just say it's categorical data. That's what it means, right? So quantitative data is a quantity. It's a number. Qualitative data or categorical data is things you can put into categories. As we think about our here, and I go through this list of things, like what's your height in inches? That's a quantitative. That's a number, right? Do you have a job where you work 10 hours? Yes or no? Your hair color. Those kind of things are categorical, right? They just put you in categories. Okay. So it's important we understand the difference. If I want to say what's the average, hair color in here, you can't really add brown plus red plus black and divide by 3, right? Doesn't make any sense. So sometimes, depending on the type of data you have, depends on the statistical tools and things you can do. All right. So let's consider all of you are the individuals. And let's look at a list. You have 4, I think, at the bottom, and then the next 3 are onto the back. So what I want you to do is consider these, and I'm going to have you do it by yourself first for just 2-3 minutes, and then we'll partner up to compare answers. First, you have to decide, is the thing listed, is it a variable? For this class, all of you are the individuals. Does this thing vary? 1. And if it does, is it a qualitative or a categorical? Now, to simplify this, to make it easier, if you think it's a quantitative, just use Q. If you think it's categorical, just use C, so you don't have to write out quantitative or qualitative all the time. We'll just go Q and C here to help us out. So first question, is it a variable? Yes or no? If it's no, you're done. If it's yes, then is it a Q or is it a C? Okay? Give you about a minute or so to do those here, a minute and a half. All right. Turn to like a person next to you, a partner across from you or whatever, just real close. Share your answers, see what you agree, and then we'll come back together. So just turn to somebody close to you. Group of partner, group of three. That's fine. All right, let's come back together here. First off, which ones are not variables? 6, teacher's age, that's good. 4. Why is the teacher's age not a variable? It's the same, right? So everybody has the same age, right? Height of the tallest student, everybody's got the same, not a variable. What about 2? The number of students with red hair. Now that's different, okay? If it was whether or not a student has red hair, so we could say, you know, do you have red hair? Yes or no, yes or no, yes or no, yes or no. But if I said, how many students in this class have red hair? I don't know, 3. I'm just, whatever. How many have red hair? 3. That doesn't change, does it? It's the same, so that also is not a variable because it doesn't change. Hair color, Q or C? C. Whether or not a student has red hair? C. Height? Q. Zip code? It's a number. That is a C. It's kind of a trick one, right? It would be similar to, think of like a uniform number in sports. Would those be quantitative or qualitative? Those would be categorical. Those would be a C or qualitative. Because realistically, you could have everybody, you know, jersey be like square, triangle, circle, pentagon would be on your jersey. And, you know, the foul was on hexagon, right? Or whatever. So it's really just a categorical kind of thing. It's not really a numerical value that matters. Or you could have A, B, C, D on everybody's jersey, right? They're not really a number kind of quantity. Now, that is true if you were the individuals. Imagine if we changed the individuals to not be you individually, but the individual will be this whole class. And now we're comparing you to Ms. Schofter's class, to Mrs. Brunker's class, to Mr. DeMassimo's class, to Mr. Pazell's class. Now, hair color doesn't make sense. Like, what's the hair color of this class? It doesn't necessarily work. But the number of red hair, wouldn't that be different for each class? So that becomes a variable. The tallest student can become a variable. The teacher's age becomes a variable. So sometimes it depends on what the individual is, on what the variable is. And that kind of stuff is usually spelled out. It's not, you know, you know what that is ahead of time. So, all right. Next, talk about, and this is a lot, like I said, a lot of fill in the blank. Continuous versus discrete data. Discrete data is a quantitative data, it's a number, that can take on a finite number of values or countable number of values. Okay. What does finite mean? It stops, right? It's a set number. You can countable. So if you're looking here, this is the thing to circle there. Discrete data is countable. Now, that could mean how many students are in the high school, right? If we sent everybody out this door in single file line, you could stand there and you could count everybody, right? Let's say I took a bucket to the beach and I scooped up some sand and put them in the bucket. Could you count the number of grains of sand in that bucket? Okay, now, so understand here what I'm talking about. It's not necessary that you physically could count them yourself, but is there a set number in that bucket? Yes, that's discrete. That's countable, right? The number of hairs on your head, that's discrete, right? You might not know how many, you pluck one off and you have one less, whatever, right? They fall out, but nobody knows how many hairs are on your head. Maybe God does, but that's right. You don't know how many, even though they are countable. So when I say countable, it doesn't mean you have to actually count them. It's just there is a set number. That's the difference, okay? The second one is a continuous data. This is data that can take on a countless number of values. Infinite number of values, so to speak. Easy way to think of another word to add, I don't have it in the definition here, but you can think about it here, is decimals. That's a good way to tell the difference. If I said, how many students are in this class? I said 24. Okay. And we did that for every room. You're not going to go down to Mr. DeMassimo's class and say, how many people does he have in his class? And you'd be like, oh, he has 17.3 students right now. You're not going to get decimals when you're counting stuff, right? So discrete data is going to be whole numbers. You can count them. Continuous is going to be like you measure something, okay? Now, one thing to understand, if I'm measuring something, let's say we use this to measure how tall you all are. Okay, this only goes to 1/8 of an inch. There's a chance that if we measured every single person's height in here, that 2 of you would be the same height if we only go to 5, 10, and 3/8, right? You're within that gap. Does that make sense? But if I would pull something like this out, you know what this is? This is a caliper, right? This is something that you can use, which you'd be able to, but the batteries are dead, so I can't use it. But that you could measure, like, how thick a piece of paper is. This goes to 0.000 of an inch. It goes to 3 decimal places of an inch. Very accurate. So if we measured all of you how tall you were this accurately, I bet none of you would be the same height, right? It'd be very hard. It'd probably depend on, where on your head we measure or where that bump is or whatever on the top of your head, right? You get a different height depending where you measure because it's that accurate of how you measure. So when you think continuous data and you think measure, think like this. Not necessarily, well, there's no decimals. I get on my scale at home and it says how much I weigh and there's no decimal points on it. Well, that's just because what you're measuring with doesn't give you decimal points. You could get on a scale that goes very, very, very accurate. And you would get all those decimal points, right? So continuous data, you're getting those decimals. It kind of goes forever, okay? So let's look at some examples. These are not in your notes, so we're just going to kind of shout them out together as we go here. Number of cups of coffee served, discrete or continuous? Discrete, you can count them. The amount of coffee in a cup, continuous, you're measuring it. The weight of a rhinoceros, it's continuous. You're measuring it. You're going to get decimals. You can't list all of the possible weights. Idea. You're going to get decimals. You're going to get that. The number of math majors at University of Findlay, discrete. The number of hits in a baseball game, discrete. Whole numbers, no decimals. The team batting average for a baseball game, continuous. You're going to get decimals. That's the idea here. Shoe size. So if you think continuous because you think 0.5 half sizes, that's true. But to go to continuous, you would also have to say, well, what size are you? And you'd be like, I'm a 9.64, right? We don't really have all possible decimal places. So we only have half size. And really, that's just the thing in the United States, right? If you look at sizes like overseas, they don't even necessarily do half sizes, right? If you have, does anybody have, looking at Luke has sandals on. What size are those? Don't they do them like in, is it millimeters or centimeters? Centimeters, right? So they do their shoes, the Birks live them by centimeters. There's no decimals, right? So that's a trick one. It's kind of like the zip code one, right? I intentionally picked one that kind of fools you at first. Okay. All right. Got a few more definitions here before we're done. First off is a population. Variable is taken from every individual of interest. The population is everybody. A sample is you only take the variables of some. So you don't actually so are you a sample or a population? Exactly. It depends. If I said of students at Smithville High School, you're a sample. If I said teenagers in the United States, sample. If I said statistics students at Smithville High School, 4th period, it's a population because you're it. So it kind of depends on what you define your population to be. If it's something like students at Smithville or teenagers or something like that, you become a sample. If it's a specific class, that would be a population. Now, let's say we measured all of you. Let's say our population is you guys. This is it. This is all that matters, right? Nobody outside this room matters. And we measured how tall all of you are. And then we added up all 24 of you, divided by 24, and we found our average height. Follow me? That average height would be called a parameter. Because that is a measure, mean, of the population. That's everybody involved. Now, imagine we took this population and we looked at some samples. So let's say we had each row as a separate sample. This row is a sample of 4. This row is a sample of 4. This row is a sample of 4. We'll pretend Brooks over here. This sample of 4. Sample of 4. And then for each row, we found your average height. So we would get 6 different values for each sample, right? And let's say our class parameter was 5'10". Wouldn't each row be different? Some rows may be a short row. That is, this. You're saying this is a tall row or short row? Okay, so this row is going to be less than our average of 5'10". We'll say maybe this row, if Brooke was over here, okay, this row would be a taller row, would probably be over 5'10". And so the idea is each sample, because of that variability, right? Each sample has its own different mean that's different from our population parameter. When it comes from a sample, it is called a statistic. So every sample has its own statistic. And each statistic doesn't have to be the same thing as a population parameter. Can a parameter change? Nope. Because if we measured everybody's height in here, and we got your height, that's what the average height is. It doesn't change. Now you could say, well, what happens if one person's not here tomorrow and somebody else is here? Does that change? Yes, but you've changed the population, right? But a parameter never changes. It's a population. It's a fixed thing based on a population. A statistic changes for every single sample. If we switched it up and we made our samples across the columns, like 6 across the column, we'd get 4 new statistics. Population parameter is still the same. It's the same thing. Okay. All right. So let's look at an example. Kind of put all this together. This is not in your notes, but we'll just kind of do it up here. A TV station wants to know what proportion of TV owners in Ohio who watch the station's new programming at least once a week. The station has a group of 1,000 TV owners in Ohio if they watch the program at least once a week. So, what are the individuals? Who are the people being surveyed or measured? TV owners, okay? What's the variable? What are they measuring? If they watch the program once a week. Is that a population or a sample? It's a sample, it's not everybody. Okay. Is that a quantitative or categorical thing that they are recording? Because they're all they're asking is yes or no. Do you watch the show? Right? If they said like how many times you watch it, then that would become a quantitative, but that's a categorical. Do you watch this show at least once a week? Yes. Okay. And then is it a stat or parameter? Stat, because it is from a statistic, some from a sample. So if you look at your notes there, if you want to, you'll notice the population, and then the third one down is a parameter. Like draw an arrow from population to parameter to kind of help you say, okay, those go together. The parameter comes from a population, and then sample goes down to statistic. Okay? You can kind of help you remember that just because of the first letter, right? Population and parameter go together. Sample, statistics go together. Okay? We do not do a lot of population and parameters to deal with that. We do a lot of sampling and statistics, as the name applies. So one of the things you have to do is we're going to use the sample and statistics to help us figure out parameters. As I've said before, what's the average height of a man in the United States? A little over 5'9". Okay. If you round to the nearest inch, it's 5'9". It's actually like 5'9" point something. Just it's not close to, just under 5. It's closer to 5'9" than 5'10". Say it that way. Did they actually go through? That's a parameter. Did they actually go through and measure everyone? No. So you have to use samples. You have to use statistics to determine things about populations, especially when populations are big, because you can't just ask everybody. Okay. All right. That really is, this is note says 1.1 and 1.2. That was 1.1. I also, this Thursday, we are going to be doing a lab, like on the computer. So I'm just giving you a heads up. I have Chromebooks back there, so you don't need to bring anything at all because you can use one of my Chromebooks. But those of you that have your own computer that you would prefer to use over our Chromebooks, just giving you a heads up to bring that on Thursday if you have one. Okay. All right. Homework. You can only do the first 5. You could probably do number 9 also, the last question. It's nothing specific. But 6, 7, and 8 deal with levels of measurement, nominal, ordinal, interval ratio, and that's where we're going to pick up with tomorrow, and that is the 1.2. We have about 2 or 3 minutes here. Don't forget M&Ms. So for tomorrow.